So Eratosthenes definitely needed the sun's rays to make his measurement. So let's come back to this question of the positions of the sun relative to the Earth and the sun's position on the celestial sphere. So let's get ourselves on a scale here. We can talk about the distance between the sun and the Earth, this distance here, and that will be 1 astronomical unit. It was defined by Copernicus first, but he didn't actually know the value. On our understanding, we know this to be about 150 million kilometers. And there's the sun again on our celestial sphere map. Recall the ecliptic is its apparent annual motion. Well, think about where we see the sun relative to the stars on that celestial sphere. This is what we call the zodiac. So, as the sun, Earth is going around its orbit around the sun, and we see where it is at different times of the year, we can project the sun onto different constellations. Right? And I'm certain some of you by now have picked out where your zodiac is around the Earth's orbit. So, things we need to emphasize here. All the zodiac is where Earth sees the sun relative to the background stars, the stars on that celestial sphere. There is no significant meaning to the position of these stars. In fact, the zodiac has changed over the centuries. There used to be 13 zodiacs, and we know that a couple thousand years from now, due to Earth's wobble in our motion, the sun will be aligned with a different set of constellations. Moving along, we all know that the seasons are connected to the Earth orbiting around the sun. So we need to be very specific here. Let's just ask the simple question. Earth seasons, are they the result of Earth's elliptical orbit around the sun? By elliptical, I mean at some points throughout the year, because of elliptical shape, the Earth will be ever so slightly closer to the sun, and other times it'll be ever so slightly further away. All right? Think for a moment, gather your thoughts. Is it this elliptical shape the source of the seasons? No. If I wanted to draw this picture to scale, it'd be almost a perfect circle. Earth's eccentricity around the sun is a tiny value, and the distance, the distance between Earth's closest point to the sun and farthest point of the sun is not a significant bearing factor on the amount of radiant energy we get from the sun. So how do we explain the seasons? We know it's connected to Earth's orbit around the sun. I say you need to think about the ecliptic plane. So let's shade this in. Right? Look at the top-down view. This would be on Earth's equator. Shade in the ecliptic plane. And now we're going to take this view and look at it from the side. Right now we're looking top-down onto the sun, and you're looking at the North Pole. Let's rotate around. There's the North Pole coming out of Earth's axis. So here's our sun. This is that ecliptic plane. So the Earth would rotate. Here it would be going into the screen, coming around, come out of the screen, and rotate out. So this is what we like to think of Earth's rotation relative to the ecliptic plane. That Earth is just revolving around, creating our 24-hour day. But the reality is that this axis here is tilted. Earth is rotating on this tilted axis relative to the ecliptic plane. And this angle should be very familiar to you. If I draw an angle going straight through the ecliptic plane relative to the angle that Earth is rotating around, we get that 23.5 degree angle back. That ecliptic angle, that 23.5 degrees, is not the sun on the celestial sphere doing this up and down on the ribbon. It's actually Earth's tilted rotational axis. And this is the direct cause of the seasons. Let's look at the Arctic summer. In the Arctic summer, the North Pole, while rotating around on the day, will constantly see the sun. The Arctic summer is in perpetual daylight. Remember the picture from a few slides ago. While the Northern Pole is in while the Northern Pole is in summer, the Southern Pole is in winter. During the Arctic winter, the southern pole does not get to see any daylight. It's in perpetual darkness for a couple of months. Now look at the relative amount of light that different sections of the Earth is absorbing. During this summer for the northern half of the Earth, more than half of the northern portions are illuminated by sunlight. The half that's tilted towards the sun is getting a lot of radiant energy, while the half that's tilted away, the light is coming in at these much shallower angles, being dispersed, spread across. All right, let's look at this from another perspective. Let's look at the light. During summer, here's the angle that the sunlight is coming in, almost straight down, right? If the sunlight was coming straight down, it would be that while it's sighing again. So the light's coming in at this very small angle, and the energy is very concentrated when you're in summertime. You're tilted towards the sun, you have a lot more straight light coming into you, there's just a lot more radiant energy for the area around you to absorb, to heat up, and that's why you get a summer. Now when you're in the wintertime, you're at the point of the Earth that's tilted further away. Once again, it's not the distance that matters here, it's that angle. When we're tilted further away, same radiant energy is coming in, but it's being dispersed over a bigger area. Summertime, that energy is concentrated. Think of any of you guys who are cruel as kids, magnifying glass and setting leaves on fire. Right? You've got a lot of energy concentrated in a small space. Things get warmer. Now we have that same amount of energy spread out over a wider area. You don't get to be as warm. You start to cool off and you experience winter time. As the Earth rotates around the sun, we can think of this picture in two ways. We can think of the motion of the Earth around the sun, and we'll label the four important points here: the vernal equinox, summer solstice, autumnal equinox, winter solstice. And we can find those same points on the celestial sphere. So let's be specific, let's define these. The summer solstice, right? On the celestial sphere, it's when the sun is the furthest north, right? Now look from this perspective. Here's the summer solstice. Boom. Summer solstice from the motion of the Earth around the sun. Then you get the autumnal equinox. Sun's on the equator and it's moving southwardly. Then you get to the winter solstice. Right? Winter solstice, the sun is the furthest south, Earth to the sun, back into our actual motion of the Earth around the sun. It's that furthest point south that you would ever see the sun in the sky. This will mark near the end of winter. Then, keep going around, the vernal equinox, when the sun catches up with the equator again. This is going to start defining the transition between seasons. Now, coming around to our poles. Currently, the North Celestial Pole is that bright star Polaris, right? But we have to talk about this fascinating thing about who's aligned up with our North Celestial Pole. Because it turns out the Earth will actually wobble on its axis. We call this precession. Specifically, the Earth's wobble, what do I mean by 26,000 years on the slide, or 26,000 years? What I mean is that as Earth is rotating around, the axis will shift. And we're going to play a little video of a gyroscope to show you what I mean by this. So let's get an idea of what the heck this precession word is. And we're going to use a gyroscope to demonstrate that. So what is a gyroscope? We're going to have this rotating axis, and we can rotate this way, up and down, or more importantly, this direction, right? And this is going to be our Earth model, right? So you are going to be looking at Earth straight on down at the North Pole. So this will be our rotation axis, and let's give this Earth a nice good spin. Right? So there's Earth spinning around, and we like to think of the rotation axis being stationary. But at some point early in Earth's formation, something perturbed this, and I'll be that perturbing force now. Notice how the Earth is still rotating around its axis, But the axis itself is doing this bobbing up and down. This is what we call the precession. See it from another perspective here. All right, rotation axis, north is now that way. And let's give it another disturbance. Boop. Earth's rotation axis is wobbling. This is the precession. As Earth's rotation axis precesses throughout the centuries, the northern star will rotate. With that gyroscope in mind, think about the Earth's precession. Another way to describe it, think of a spinning top as it's spinning around, precessing. So we could say, right now, Earth's polar axis lines on the Polaris, our current northern star. A couple thousand years ago, it would have been Thuban. And a couple thousand years from now, will eventually be Vega. That's because of this axis rocking back and forth due to that precession.